We all see the nail pull test, right? It spits out a number, but what does that number really mean? In this explainer, we're going to go way beyond just pass or fail. We're diving deep into the physics to deconstruct what's actually happening inside the board in those crucial milliseconds right before it breaks. So here's how we're going to tackle this. We'll kick things off with the test itself and a really puzzling paradox it reveals. Then we'll put on our physics hats for a bit and really dissect the forces at play. After that, we'll watch the whole collapse happen in a 4-stage sequence. And finally, we'll zoom all the way in to find the true weakest link on a microscopic scale. All right, first up, the standard test. And more importantly, a very counterintuitive problem it brings to light, especially when we try to lightweight our products. We all know the procedure, ASTM C473. Now, on the surface, it looks pretty straightforward. We apply a load at a constant rate and just measure the max force it takes to yank a nail head right through the board. Simple, right? Well, not exactly. See, this simple test uncovers a really complex problem. As we make our boards lighter, by making them more porous, the strength doesn't just drop off in a nice, neat line. It falls off a cliff. So what is really going on inside that material? And here's the heart of the matter. You take out just 10% of the weight, and you can see a drop in nail pull strength of over 20%. This is what we call the density paradox. And honestly, it's the biggest challenge we face in lightweight formulation. Getting this right is everything. And the research gives us our first big clue. The answer isn't about the board as a whole. It's all about how the core itself responds to stress. To be specific, it's the collapse of that foam structure, the core compaction, that's the real bottleneck. That's the limiting factor. Okay, so if the core is compacting, how does that collapse actually start? Well, to get that, we need to really visualize the incredibly complex stress state that the nail head creates the very moment it touches the board. Yeah, it's not just one simple push downward. It's actually 3 different forces all acting at the same time in different directions. In mechanics, this is called a triaxial stress state, and understanding this is the key to unlocking the whole puzzle. So the first force is the most obvious one, vertical compression. This is the one we all picture, right? The direct downward pressure just squeezing and crushing that porous gypsum right under the nail. Now things get interesting. Because of something called Poisson's effect, which basically says if you squeeze something, it bulges out to the sides, that vertical crush creates outward forces. The core wants to expand sideways, which pulls the face paper tight, kind of like the surface of a trampoline. And finally, there's a third force. Right at the sharp edge of the nail head, you get this intense shear stress. Think of it like a powerful slicing force that's trying to punch a clean circle right through the paper and the core. Okay, so here's the crucial part. These 3 forces don't just cause one single instant break. No, they trigger a super fast, totally predictable sequence of events, like a chain reaction of failure that, thanks to incredible tech like X-ray tomography, we can actually watch happen. See, failure isn't just one thing. It's a 4-stage process that's over in a flash. It starts with a flex, then a crush, then a crack, and finally a total collapse. Let's break each one down. In stage 1, everything behaves pretty much how you'd expect. The paper gets tight, the core squishes a little, but it's still elastic. If you took the load off right now, it would pretty much spring back to its original shape. No permanent damage done yet. But here, in stage 2, we hit the point of no return. This is the critical phase. The weakest little bubbles in the foam structure buckle and collapse, forming this dense plug of crushed gypsum right under the nail. We call this the crush zone, and it's what absorbs most of the energy right before the big failure. Now, once that crush zone gets deep enough, the whole failure mode changes completely. The stress isn't contained in that little spot anymore. It shifts to what we call bulk shear, and a massive crack starts to form, spreading out and down from the edge of that dense plug. And the result is this beautiful cone shape you see here. This isn't a guess. CT scans, simulations, they all confirm it. The failure spreads out as a shear comb at a really precise 30-degree angle. This is the classic signature, the smoking gun, of a nail pull failure. That cone is what leads directly to the final stage, punch through. This is where you get a catastrophic loss of strength. The nail and that whole cone of gypsum it created are just shoved right through the rest of the board.
the load it can carry drops instantly to zero. Game over.
So, if that's the whole domino effect of collapse, what knocks over the first domino? What actually determines when that initial core compaction starts? Well, for that, we have to zoom in. I mean, way, way in, down to the microstructure of the core itself. And it turns out, the board's resistance isn't really about its overall bulk density. It's about the very specific shapes and features that act as starting points for failure, what we call critical defects. It all comes down to the geometry of the foam. And this slide just lays it out perfectly. On the left, you've got a champion core. You can see these strong, thick pillars of gypsum between small, uniform bubbles. The walls around the voids are dense and tough. But on the right, that's a disaster waiting to happen. You have huge, irregular voids that concentrate stress, and the walls between the bubbles are thin, fragile, and just waiting to buckle. So here's what I really want you to take away from all this. Nail pull failure is a predictable 4-stage game, and the most important move in that game is core compaction. That's the real limiting factor. So to solve that density paradox, to make stronger, lightweight boards, we have to stop just thinking about bulk density and start engineering the microstructure. It's about building better, stronger walls and pillars at the microscopic level. But this brings us to one last, really critical question. We spent all this time talking about the core. But a super strong core doesn't do you any good if the paper peels right off it, right? The core is only half of the system. So what happens when the bond, the interface, is actually the weakest link? We're going to dive into that critical bond in our next module.